Hi everyone, it's Mr. Zarzak. We're back down in my basement, in the dark, bringing you another episode of Physics Underground. In this episode, we're going to look at the additive and subtractive rules for color mixing. So, let's get started. Okay, so the first thing I want to talk about is what's called additive color mixing rules, which are the rules that govern light that's emitted. So from like a light bulb or from the sun or from a candle flame or in this case an overhead projector. Okay, and so I'm using this overhead projector and notice I've got a prism on top of it. You'll see why I use that in just a second. Okay, but the overhead projector is just a source of white light. Okay, a misconception is that white is a color on its own. Okay, but in actuality, white is really our perception of all the colors of what we call the visible spectrum, and that's what the prism is for. It's to separate out the colors into the visible spectrum. So I'm using that to make a little color. And I'm going to try to block out some of the ambient light, okay, from the overhead projector, just so that hopefully this is a little bit clearer, so that you can see the colors of what we call the visible spectrum. If you're familiar with Roy G. Biv, that's red, orange, yellow, green, blue, indigo, and violet. We don't really see the indigo per se in the spectrum. That's a conversation for another day, but we can certainly see some reds and some oranges and some yellows and some greens and some blues and some violets. Okay, so that's the first part, is that white is a combination of all the colors of the visible spectrum. So mounted to this stand here, I have a little spotlights with three colors, red, green, and blue. And the reason that we have red, green, and blue is because when it comes to what we call the rules of additive color mixing, which is the physical rules governing emitted light, red, green, and blue are our primaries. Primary means one, okay? And so just by taking and turning these little dials, I can turn up the red, the green, and the blue, and I can vary their intensity too, all right? And so what I'm gonna do is turn the lights off so that you can see what these look like when they're cast onto my white wall back here. So let me turn off the lights. All right, and now with the lights off, this is primary red, green, and blue. So if you've heard of RGB, that's what it stands for. The acronym is for red, green, blue. All right, these are primaries. So this is our first order colors, and these are the most useful colors that we have in the visible spectrum for making other colors. When you combine two primaries, you get what's called a secondary color. So if I mix red and green together in equal parts, I get yellow. Yellow is a secondary color, all right, which is the combination of two primaries. Okay, most people find it surprising that red and green in equal parts but make yellow, but they certainly do. And if I put my hand in front, let's see here, get the shadow in the right spot, you can actually see, if you look really close, okay, the different sides of my finger have the different shadows of green and red. All right, depending upon the angle and which light that's getting blocked. So you can see that the yellow really is the combination of those two lights. All right. If I take off let's turn off the green. Actually, let's leave the green on and put that together with the blue. Okay, so this kind of blue-green color that we get right here is called cyan. That's C-Y-A-N. All right, which is the combination. So this is our secondary color. So we've got yellow, cyan, and then the third. It's kind of interesting in that, here, let's turn off the green and turn on the red. Okay, so this kind of pinkish purplish color that we get here, we call this magenta. What's interesting about this is on the visible spectrum, if you pay attention to it next time you see a rainbow, you see that one side of the spectrum is the red side and the other side is the blue-violet. Okay, and so in nature, magenta does not occur naturally in emitted white light. We have to create it. And so our minds are inventing this color magenta by overlapping these two colors of blue and red together. It's pretty cool, all right? But anyways, if I turn the green on, if I combine equal parts red, green, blue, okay, well here's why we really use these as our additive primaries, is that if we mix all three in equal parts, we get white light, okay? And that's the idea, is we can recreate white light from just these three primaries. Now, our primary colors are red, green, and blue. Our secondary colors are yellow, magenta, cyan. Okay, all three of those make white light, but then something kind of interesting happens here. Okay, we have a third category that we find useful, which are called complementary colors. Complementary colors are two colors that can be put together to create white light. All right, and so let me turn off the blue here for a second. Okay, so that we look at the combination of red and green. Okay, so that makes yellow. So this whole space here is yellow light. Well, what color can be added to yellow light to make white light? Well, it's the primary that's missing. And so if I add blue light, if I layer that on top of yellow light, I actually get white. Okay, very counterintuitive that it would be mixing blue and yellow together would make white light, but it does. Those are what we call complementary colors, and the way to find them is we just look across the color wheel at the primary and the secondary that are directly across from one another. So if blue light and yellow light can be used to make white light, look at this. Okay, blue light and red light make magenta. So this pinkish purple kind of color, if I want to make white with magenta, the color that I need to add to it is green. Green and magenta are complementary colors because if I add some green to some magenta light, I get white light. Okay, very weird, but also totally true. We can see it right in front of us. And then finally, all right, I'm going to, excuse me, let's see, we did magenta. All right, so let's just take off the blue here. Actually, I'm sorry, let's take off the red. There we go. Okay, that's the one we're missing. Okay, so if I wanted to take cyan light, all right, and I wanted to use that to make white light, I would add red to it. Red plus cyan makes white light. Very strange that this red color and this blue-green put together would give you white light, but it does. Okay, so these are the rules for additive color mixing. Your primaries, red, green, blue. Your secondary colors, yellow, magenta, cyan. Your complementary colors, which is what you get to make white light. You can take yellow and blue. You can take magenta and green. Those are complementary colors. Or you can take cyan and red combined to make white light. All right, so those are your rules for additive color mixing. Okay, so when we use spotlights or emitted light, we follow what's called the additive rules for color mixing, in that we're taking our primary colors of red, green, blue, and we're adding them together to make other colors, and if we add them all together in equal parts, that red, green, blue, we get white light. All right, well, what about like a book or a t-shirt? Okay, those come in all kinds of different colors, but none of them emit their own light. All right, well, the reason that we see something, say, as red is because, well, it's going to reflect red light and it's going to absorb the other colors that hits it. And when I say absorb, really what that means is it becomes thermal energy, turns them into heat, okay? A white background here, something that's white, is going to reflect all the colors of the visible spectrum equally, which is why on a hot day, you'll actually stay cooler if you wear a white t-shirt as opposed to a black t-shirt. Okay, dark colors tend to absorb a lot of that visible light and turn it into thermal energy, which is heat, okay, to keep it simple. These colors, yellow, magenta, cyan, red, green, and blue, okay, these are our primaries and these are our secondary colors. So for this set of rules that we call subtractive color mixing, okay, the primaries and the secondary colors are actually flipped. All right, the reason that it happens this way, well, you really need to see this under the spotlights. So let's get the room dark and let's get these dots up here one at a time so you can see what I'm talking about. All right, so I've gone ahead and taken away all the dots except for the yellow one. Okay, so this is a pure yellow pigment. This is one of what we call our subtractive primaries. The reason that it's called a subtractive primary, all right, is, well, yellow looks yellow because it reflects reds and greens and absorbs blues. So right now I have it under white light, so I've got all three of the spotlights on so that you can see the yellow on the white background. Look what happens when I turn off both the green and, oops, actually that's not what I'm doing. Look what happens when I turn off the green and the red and I just put on the blue. Okay, that's that same yellow dot under blue light. It looks very black because, well, yellow absorbs blues and reflects reds and greens. There's no red and there's no green light to reflect, so it's going to absorb all that blue light. It's going to make it look very black. All right, if I take and I put on instead, say, the green light here, okay, well, yellow will reflect green and red and it'll absorb blue. So what you're seeing is that yellow dot is reflecting all that green light, which means that that yellow light under green light looks green. And you can see that the white background looks very green too, so it becomes kind of difficult to distinguish where the dot ends and the paper background begins because they both look green under green light. Likewise, if I turn off the green and I turn on the red, okay, you can see that, well, that yellow dot looks very red under red light, as does that white background. Those are both reflecting out all that red light. All right, very, very cool. If I take and I turn the green back on, okay, well, now both the paper and the dot are under yellow light, so that you can kind of see a little bit of contrast there, but both the paper and the dot are looking yellow, so like the yellow dot's going to look yellow under yellow light, okay? let's turn the green off. Now let's turn on the blue. Okay, so now what I've got here is I got magenta light shining on that yellow dot, but that yellow dot is going to be reflecting back the red. There's no green to reflect back to make that yellow color, and so we see that under magenta light, the yellow dot is going to look red because it's going to reflect the red and it's going to absorb the blue. All right, if I instead turn off the red light and turn on the green, okay, well now I've got cyan light shining on the yellow dot, which is a combination of blue light and green light, but a yellow pigment is going to absorb out all that blue light and reflect the green light. Okay, so the point is that we call this a subtractive primary because that yellow pigment, it does one thing: it subtracts out blue light from white light, and it reflects out everything else. Okay, so you can see it one more time. This is the yellow dot just under blue light, looks black. All right, because that's what the yellow primary does. It absorbs out blue. All right, let's switch this up now. I've gone ahead and replaced the yellow dot with the magenta dot. Okay, magenta is our second subtractive primary. Okay, it's a primary because what it's going to do is it's going to absorb one additive primary out of white light. Okay, so I've got red, green, and blue on it. All right, and so if I take out the blue and the red, which are the colors that make magenta, the only thing that's left is green, and that's exactly what a magenta pigment is going to absorb away. And so under green light, magenta looks black. Remember, magenta is red plus blue, so if I'm only shining green on it, there's no red or blue to reflect all that green light. It gets absorbed, that magenta dot looks black. All right. If I take, and here let's do the blue, that'll work. Okay, so under blue light, that magenta dot's gonna look very blue because what is magenta? Magenta is red plus blue, and so I've only got blue to reflect off of it, so all that blue light's being reflected off. Notice that the background looks blue too, so it becomes kind of tough to distinguish, okay, really what's going on here. We've got two blues that were layered right on top of one another. Let's take on and turn off the blue and turn on the red. Magenta under red light is just gonna look red, just like that white background is. Both the white and the magenta are both gonna reflect out that red, so it becomes really difficult, okay, to distinguish the white background from the magenta dot because they both look red under red light. All right. If I turn on the blue light, okay, well now I'm shining magenta light on a magenta dot, which looks, well, magenta. It's going to reflect out both that red and that blue. The background is going to look magenta as well. So again, it becomes a little difficult to really tell where the dot ends and the paper begins, okay, because they're both going to look magenta under magenta light. All right, let's turn off the blue and turn on the green. Okay, so remember, magenta absorbs out green light. So if I shine red and green on the magenta, in other words, if I shine yellow light on the magenta, under yellow light, the magenta looks red because it's going to reflect out the red and it's going to absorb the green. Remember, that's what the magenta pigment does. It takes away one primary of emitted light, which is it takes away the green. All right, and then finally, let's take off the red and turn on the blue. All right, so this is magenta under cyan light. Okay, and so what we're going to see is that magenta dot is going to look blue under cyan light because it's going to reflect out the blue and it's going to absorb out the green. All right, very cool. All right, let me just turn the red back on so that you can see the magenta dot under white light one more time. I now have our third subtractive primary up on the board here, which is cyan. Okay, so what makes cyan a primary pigment is that it absorbs red and only red and reflects blues and greens. So if I turn off the blues and the greens here, okay, and I leave just on the red light, you can see that the cyan dot looks pretty darn black under only red light because that's what the pigment's doing. It's absorbing just that red light. Okay, remember, primary means one, so it absorbs one primary. If I turn off the red and I turn on the green, okay, well then cyan is going to look very green under green light. And if I turn on the blue, cyan is going to look very blue under blue light. All right. If I turn on the green light now, so if I put cyan light on cyan dot, well, it just looks cyan. And let's see here. Let's leave the green on, and we'll turn on the red. Okay. So the cyan under yellow light, okay, is going to look green because it's going to absorb out that red light. Remember, that's what primaries do. They absorb one primary and it reflects the green. So it absorbs out the red and it reflects the green. And then finally, If I turn on the blue and I turn off the green, okay, well then we see that under magenta light, that cyan looks very blue, all right, because it's going to absorb out that red and it's going to reflect the blue, all right. So just so you can see it underneath the white light again, okay, we see it as cyan because that dot is reflecting out the blue and the green and it's absorbing the red. With subtractive color mixing, which is the rules that govern reflected colors, so things that we print or dye, yellow, magenta, cyan, those are our primaries, whereas red, green, and blue are our secondary colors. Okay, so it's reversed from our additive rules. So what I have up here is this red dot right now that's printed on this piece of paper, and the way that it was able to be printed was by putting down equal parts of yellow pigment and magenta pigment. Those two together gets you this red dot. The yellow is going to absorb away blue light from white light. The magenta pigment is going to absorb away green light from white light. And so the only thing that's left to be reflected, the thing that's commonly reflected by both yellow and magenta, is red. Hence this appears red. Let me show you what I mean. All right, so first we'll just turn off everything except for the red light. Okay, and so the red dot looks red under red light, as does the white paper in the background. So you see it's very difficult to even see the dot at all. There's no contrast between the paper and the dot. All right, so now let's take off and turn off the red light. This is red dot under green, and it looks black. That's the magenta pigment absorbing out the green light. This is the red dot under blue light. That's the yellow pigment absorbing out the blue light, makes it look black. Under blue, green, so that's cyan light. Both make them look black because it's absorbing out both the blue and the green. There's no red to reflect. Two primaries absorbed out, one primary reflected. Red is a secondary color, okay? Our next secondary color for subtractive color mixing is green. So there's a green dot printed on this white piece of paper. The way that we get this green dot is by putting down two layers or equal parts of pigments, okay, of yellow and cyan. The yellow pigment absorbs out blue light from white light. The cyan pigment absorbs out red light from white light. And the color that is commonly reflected from both yellow and cyan pigment is green. All right, and so let me show you what I mean. So first, let's just turn off everything except for the green. So you can see the green dot under green light looks, well, green. All right, now let's look at the green dot under blue. Okay, very, very dark. Compare that blue dot to the rest of the black area outside of the circle. Okay, and you can see that that green dot looks very black. And if I put it under a red, I get the same thing. That green dot's going to look very black. Looks the same as the area outside of the red circle. All right, so we call it green a secondary color because it absorbs out red and it absorbs out blue and it reflects a green. Okay, so if I put it under magenta light, well, magenta is not green. Okay, magenta is red and blue, and so that green dot still looks very black under red and blue light. If I take off the blue and I turn back on the green, okay, that green dot under yellow light is going to look green. It's going to reflect out the green light, and then it's going to absorb out the red. Likewise, if I turn off the red and turn on the blue, so I illuminate the green dot under cyan light, that green dot is going to look green under cyan light because it's going to reflect out the green and it's going to absorb the blue. And so here's our second secondary color, green under white light. Last but not least, okay, we have our third secondary color for subtractive color mixing, which is blue. So we've got the blue dot printed on the paper. The reason we're seeing this as blue is we've got equal parts pigments of both cyan and magenta. The cyan pigment is going to absorb out red light from white light, and the magenta pigment is going to absorb out green light from white light. The only common reflected color between those two subtractive primaries is blue, so we see the dot as blue. All right, so if we go through it all again, I'm going to turn off the red and the green here. So the blue dot under blue light looks, well, blue, not surprising. The blue dot under green light looks black because there's no blue light to be reflected. All right, the blue pigment is absorbing out the green. And the blue dot under red light looks black as well. Again, the combined blue pigment there absorbs out reds and greens, so it's going to absorb out all that red. All right, if I turn back on the green, so if I put it under yellow light, okay, so the blue dot still looks very black. Okay, it's going to absorb both the red light and the green light. If I turn off the red and I turn on the blue so that we illuminate the blue dot under cyan light, the blue dot looks blue because it's going to reflect the blue and it's going to absorb the green. And if I take and I turn off the green and turn on the red so that I'm illuminating the blue dot under magenta light, the blue dot looks blue. It's going to reflect out the blue light. It's going to absorb the red light. Okay? And so here's our third subtractive secondary color under white light, blue. All right, so once again, we have yellow, magenta, and cyan, which is our primary colors for subtractive color mixing, rules which govern paints and dyes and printing. And our secondary colors are blue, green, and red. I've got them arranged this way so that the primary and the secondary color that are complements of one another are paired together. Well, what I mean by this is with subtractive color mixing, if I just look at the primaries here, okay, yellow is going to absorb away blue, magenta is going to absorb away green, cyan is going to absorb away red. So if I mixed equal parts yellow, magenta, cyan pigment, I would make a pure black. All right. Likewise, I could do the same thing with red, blue, and green pigments, all right, but it's a lot more expensive because in order to get to a blue, I first have to combine two of my primaries to make that secondary. All right, to make that blue pigment, I would have to combine magenta and cyan. Okay, so the same is true for both green and for red. To make the green, I would have to put together yellow and cyan, and then to make the red, I would have to put together magenta and yellow. Well, anyways, so these two are complements of one another because if I put those two together, I would also get black in that the yellow would absorb away the blue, and then the blue would absorb away the red and the green, so there'd be no colors left, so we'd see that as a black pigment. Okay, the same thing I could do with the magenta. The magenta would absorb away the green, and then the green would absorb away the blue and the red, so put those two together, you have black, those are complements. And then with the cyan pigment over here, the cyan would absorb away the red would absorb away the green and the blue. Again, you put those together, you got a black pigment. All of that is extremely expensive. And so when we do printing, we take advantage of natural black pigment, which comes from carbon. And so if you're familiar, if you've got a color printer at home, you know that there's a color cartridge and there's a black cartridge. And so we call this YMCK printing, yellow, magenta, cyan, and then the K actually stands for the black cartridge. The K gets used as the last letter in black so that you don't get confused the B for black with blue. All right, this is Mr. Zarzak down in the basement saying thanks for watching another episode of Physics Underground, and we'll see you next time.